Before I officially start this lesson, I would like to share a story with you. So, when I was a child, so di naman talaga dapat ako mag-engineer. So, gusto ko nun talaga at may architect ako. Nagdodrawing ako mga building. Tapos, gusto ko mga landscaping, ganon. Kasi yung parents ko, landscape yung business nila. Naging engineer lang yung pangarap ko kasi naalala ko noon na gusto ko rin talaga mag-drawing. Lumaban din ako sa mga drawing competitions. Pero, nahiligan ko rin yung math dahil sa mga teachers ko noon na pinakita sa akin yung kagandahan kung paano mag-solve ng math. So, after nung mga competition sa drawing, nung una talaga, natatakot pa ako sumali sa competition sa math. Ayun, nung unang sali ko nun lala ko nun mga patala talaga ako nun. Second to the last place. Pero, at that time, naalala ko nun, dapat talaga susukuan ko na siya. Pero, sabi ng teacher ko, tuloy lang, laban lang. And ayun, after few years, mga 6 years ganon, to be exact, ayun, naging champion din ako sa isang competition sa math. Then, at that time, nung grade 10, sabi ko, pwede naman pala ako maging engineer. Tutuloy ko na lang yung pangarap ko na maging architect. Kasi di ba may mga buildings naman din doon. Tsaka makapag-drawing ka pa rin. Pero with math na rin, di ba? Like, yun yung parang hitting two birds with one stone. Pareho akong gusto siya. Kaya, ayun, nandito na ako sa math. Sa engineer pala. Ayan. So, ngayon, nasa college na tayo. Konting taste na lang, di ba? Nasa na tayo? One step away na lang, di ba? For achieving our dream. So, let's start. So, para sa brief history ng Geotechnical Engineering, Geotechnical Engineering is a significant discipline in the modern world. Isa siyang ng branch ng civil engineering that deals with the behavior of earth materials, diba? Geo nga, diba? Earth. Yan. To ensure that the structures we build today are able to stick over the surface of the earth without tilting or sinking into the soil. Without geotechnical engineering principles, our roads, homes, dams, and many other structures would literally be swallowed into the ground. So, nung mga unang panahon, konti lang talaga yung ng geotechnical engineering. More or less, ginagamit lang siya sa irrigation and sa farming, ganon. Pero nung medyo nag-advance na yung geotechnical engineering and dumating din yung Tower of Pisa, ayun, maano nyo mamaya, ma-explain yun mamaya ng mga kagrupo ko na nagtitilt. Ayun, napansin nila na yung lupa rin is maalaga rin siya sa construction. If you will ask the father of geotechnical engineering is Carl Terzaghi. As he put it himself, all the modest achievements which I have to my credit can be described by a simple formula. Guided by common sense and casual observations, I recognized weak points in traditional procedures and tried to make them less weak. Sometimes I failed, but usually I succeeded. What is geotechnical engineering? So, gaya nga ng sinabi ko kanina, geo means earth. Geotechnical engineering is a branch of civil engineering that focuses on the behavior of soils under the influence of loading forces and soil-water interactions. Foundation built for above-ground structures include shallow and deep foundations. Mamaya, madidiscuss natin yan. Yung shallow and deep foundations and yung mga types under nila. Retaining structures include earth-filled dams and retaining walls. Earthworks include embankments, tunnels, dikes and levees, channels, reservoirs, deposition of hazardous waste, and sanitary landfills. Geotechnical engineering is also related to coastal and ocean engineering. First, coastal engineering can involve the design and construction of wharves, marinas, and jetties. Second, ocean engineering can involve foundation and anchor systems for offshore structures such as oil platforms. Moving on, so ano nga ba ang ginagawa ng geotechnical engineer, if you may ask? The role of a geotechnical engineering are the following. They are responsible for signing off on a project's feasibility. Second, they prepare and inspect projects involving drilling and exploration. Third, they run a series of tests and evaluations to ensure the land can support the proposed construction. They investigate the following. First, the composition of your foundation soils, including the material, bedrock, rocks, and soil layers beneath the proposed construction location. Second, the geological and geotechnical feasibility of your site and relation to surrounding sites. Lastly, groundwater conditions and water flow paths and how they affect the development. So here are some questions that geotechnical engineers answer. First, how tall can we make a building on this ground? Second, can we build a road here? Third, if we cut through this mountain, will the slope collapse down onto the road? Moving on, ano nga ba ang kahalagahan ng geotechnical engineer? Nandyan lang ba sila para lang tumambay or maghakot ng lupa? Ganon. The following are the importance of geotechnical engineering. First, it helps prevent complications before they happen or even long after construction. Second, it guides you on water mitigation, building placement, and how surrounding structures such as walkways and parking lots will affect your project. Third, applied in military, mining, petroleum, and other engineering disciplines that are concerned with construction occurring on the surface or within the ground. Lastly, without geotechnical engineering, buildings could lean, settle, and eventually collapse as the earth below them shifts. Next, we move on to the deep and shallow foundation. So natapos na natin yung first part, which is yung preliminaries. So dito sa section na to, hindi naman lahat ng building so same foundation, no? Nakadepende siya sa type ng lupa or type ng structure na ating itatayo dun sa lupa na yon. The first type of foundation is deep foundation. Deep foundations are required when building on sand and other subsoil that will not be able to absorb the load of the building. Instead, a foundation must be established deep underground or even underwater, where contact with stronger layers of the earth can be established. Bridges, piers, and dams, for example, must lay foundations underwater while still retaining structural integrity. This is where deep foundations become essential to the construction of large structures. The second type of foundation is shallow foundation. Typically, a shallow foundation is one that is wider than it is deep. Shallow foundations can also be called spread or open footings. For obvious reasons, shallow foundations are the more economical of the two types. They don't require much in the way of digging or boring into the earth, and for that reason, they are the most common. Shallow foundations are useful when the building isn't exceedingly heavy and the soil can bear a significant amount of weight at a shallow depth. Now, we'll move on to the examples of shallow foundation, which are mat, individual footing, combined footing, and stem wall. Each has a unique structure and various use cases. As you can see on the pictures, there are mat foundations, stem wall foundation, and combined footings. Yung individual footing is parang siyang combined footing pero mag-isa lang yung foundation. So parang ganun lang yan. The first type of shallow foundation is mat foundation. A mat foundation takes full advantage of the surface area where the building will be erected, essentially using the basement as the entire load-bearing foundation. Mat foundations are often used when the soil is loose, weak, and requires the weight to be distributed evenly. Mat foundations are also used when a basement is feasible and the pillars or columns are spaced close together. It is often referred to as raft foundation because the basement foundation is submerged in the soil, like the hull of the raft in water. Second, under the types of shallow foundation is individual footing. It is one of the most common types of shallow foundation. It might be even what comes into mind when you think of a foundation. Individual or isolated spread footings are typically square, rectangular, or even a geometric frustum block of concrete that carries the load of a single column or pillar. The width of individual footing depends on the weight that will be carried and the bearable capacity of the soil. Third, for the shallow foundation is the combined footing. A combined footing is very similar to an individual footing, except one base shares the weight of two pillars or columns that are close enough together to warrant a shared foundation point. Lastly, under the shallow foundation is the stem wall foundation. A wall, strip, or continuous footing is a foundation that runs the entire length of a load-bearing wall. The strip footing is usually 2 or 3 times the width of the wall in question and is usually built with reinforced concrete. These foundations are typical when the building's weight is distributed on load-bearing walls instead of columns, pillars, or beams. Strip foundations are commonly used to build masonry walls, but can also be used effectively when building on gravel or tightly packed sand. Okay, natapos na natin yung shallow foundations and yung types under nun. Moving on, the examples of deep foundation, ayan na. Deep foundations are more commonly used for larger structures, but can be used for homes built on steep cliffs, over water, on the beach, or other unique locations. Deep foundations are built exactly where they sound. Deep into the earth. Sa pinakailalim talaga, no? Malalim. Ganun. The main examples, pile and caisson, also have some subtypes, which we'll also cover later. Here are the examples of deep foundation, which are pile foundations and caisson foundation. The first example of deep foundation is the pile foundation. This is the most common among the deep foundation category. There are 2 types of pile foundations. The first one is end-bearing foundations, and the second one is friction piles. Both consist of boring large, sturdy columns deep into the ground. So in end-bearing piles, sometimes the soil that we build on will never bear enough weight for the project styles being built, even with dirt compactors and shallow foundations. Instead, we must bypass this layer of subsoil and get to the substrata of bedrock beneath to distribute the load. End-bearing piles are driven as deep into the ground as necessary for the end to make contact with the rock layer within the earth. This allows the load to be passed through the piling and into the rock, creating a safe distribution of weight. Second, friction piles. Friction piles take a different approach to the contending layer of subsoil. Instead of boring down to the layer of the rock, the principle behind friction piles is an exchange of forces with the soil surrounding the column, taking full advantage of the surface area of the column. The amount of weight a friction pile can sustain is directly proportional to its length. Every pile has a zone of influence and must be spread consistently to ensure even distribution and absorption of weight. Piles can be made out of wood, concrete, or H-shaped steel. Piles can either be prefabricated and driven into the ground or cast in situ. Cast in place or on site, no, sa job site. The second type of deep foundation is the Gaussian foundation. A Gaussian foundation is most often used in construction of a bridge, pier, or other structure over water. But it can also be used to support freeway overpasses, hillside homes, and more. Gaussians can be prefabricated, floated to the drilling site, and placed in a dredged pit. Gaussians can also be built on site with a mesh grid of rebar filled with concrete. To build a Gaussian foundation, the loose land is dug with an auger until bedrock is reached. While digging, a hollow steel casing can be implanted to prevent the sand or soil from caving in on the progress. The reinforcing mesh rebar is then centered within the casing and concrete is poured, starting at the bottom and filling up the casing, forcing the remaining groundwater out the top. Once the concrete has adequately filled, the casing can now be removed. Under Gaussian foundation, there are few variations of the Gaussian. Here are the main examples. First is open Gaussian. A box without a bottom sunken into the ground and stabilized with weights for ballast and a mock tube to remove excess groundwater. The pressurized chamber allows work to be done inside. Second, pneumatic Gaussian. When maintenance work needs to be done deep underground or underwater, these Gaussians are built to enable workers down the shaft. Third is the monolithic Gaussian. Large single-column Gaussians made of reinforced concrete. Fourth is sump Gaussian. Gaussians with the ability to pump water from below, often used by offshore oil drillers to recirculate contaminated water. Fifth and last type is the box Gaussian. A hollow concrete box with bottom and sides is submerged and subsequently filled with concrete. In its hollow state, the box is less dense than water and is at risk of floating out of position. But once filled, it is more permanent. So, you may ask, Marami tayong foundation types na discuss, di ba? So, paano nga ba pumili ng tamang type ng pundasyon na gagamitin para sa building or structure? Depending on the size, location, and geotechnical challenges facing your project, the decision to build shallow or deep foundations may be clear, but the exact type of foundation may be more nuanced. Given the importance of a building's foundation to its overall structural integrity, getting this decision right is essential. Use qualified construction companies, engineers, and consultants to verify the foundation is sound and will bear the load for the structure's life. You should also ensure the lines of communication between everyone involved with the project is clear. Okay, so tapos na tayo dun sa types ng foundation and yung under none. Moving on for the third type, which is different types of soil. So, maikli lang to, no? Di katulad nung nauna. No? Sana buhay pa kayo dyan. Soil can be defined in many ways. In civil engineering, soil is a naturally occurring, loose, uncemented, or weakly cemented, or relatively unconsolidated mineral particles, organic or inorganic in character, lying over the bedrock, which is formed by weathering of rocks. Soil is formed by different particles such as gravel, rock, sand, silt, clay, loam, and humus. The first type of soil is sand. It is the most extensively used construction material. It consists of particles of rock and hard minerals such as silicon dioxide. They are the largest types of soil particle, where each particle is visible to the naked eye. The large, relatively stable sand particle size increases soil aeration, improves drainage in tight soils, and creates plant growth supporting qualities or tilt. The sand particle size, of course, sand ranges from 2 to 4.75 mm. Medium sand ranges from 0.425 to 2 mm, and fine sand ranges from 0.075 to 0.425 mm. The bigger particle size of the sand gives wet or dry sandy soil a grainy texture when you rub it between your fingers, and it makes the soil light and crumbly even when you try to stick it together in your hand. The particle shape is angular, subangular, rounded, flat, or elongated. The texture is rough, smooth, or polished. The second type of soil is silt. Silt is a sediment material with an intermediate size between sand and clay. It is carried by water during flood. It forms a fertile deposit on valleys floor. The particle size of silt ranges from 0.002 and 0.06 mm. Silt is a non-plastic or low plasticity material due to its fineness. Due to its fineness, when wet, it becomes a smooth mud that you can form easily into balls or other shapes in your hand, and when silt soil is very wet, it blends seamlessly with water to form fine, runny puddles of mud. The third type of soil is clay. Clay particles are the finest of all the soil particles, measuring fewer than 0.002 mm in size. It consists of microscopic and submicroscopic particles derived from the chemical decomposition of rocks. Clay is a fine-grained cohesive soil. They stick together readily and form a sticky or gluey texture when they are wet or dry. Clay is made of over 25% clay, and because of the spaces found between clay particles, clay soils hold a high amount of water. Clay expands when in contact with water and shrink when getting dry. Compared to sand particles, which are generally round, clay particles are thin, flat, and covered with tiny plates. Organic clay is highly compressible and its strength is very high when dry, which is why it is used in construction as mud mortar. Okay, for the last type of soil, which is loam. Loam is a mixture of clay, sand, and silt, and benefits from the qualities of these three different textures, favoring water retention, air circulation, drainage, and fertility. These soils are fertile, easy to work with, and provide good drainage. Depending on their predominant composition, they can be either sandy or clay loam. The way other particles combine in the soil makes the loam. For instance, a soil that is 30% clay, 50% sand, and 20% silt is a sandy clay loam. With the soil types before loam listed in order, their particles are most dominant in the loam. The labels clay loam, silt loam, and sand loam are used to refer to soils that are composed predominantly of those ingredients. So okay, natapos na natin yung different types of soil. Okay, promise, ito na yung last para sa part ko, which is the 4 types of geotechnical testing. So let's start. So yung unang type nito is the test pits. Test pits are much like you would expect. A pit is dug either manually or with an excavator in order to reveal the subsurface conditions to the depths desired. Second one is trenching. Trenching is similar to test pits, except that in this case, the pit is elongated over some distance in order to establish how the subsurface conditions change over various parts of the work site. Third is boring. Borings, usually deployed by a drill rig and drill crew, can vary in diameter and provide the opportunity to assess density through standard penetration testing or SPT to physically remove soil or rock samples for assessment and testing. So, ito, yung boring machine, ito yung nakikita nyo sa paggawa ng MRT ngayon. Yung binubutas yung ilalim ng lupa talaga. And the fourth and final type of geotechnical testing is the in situ testing. In situ testing or on-site testing methods include penetration tests such as SPT, which penetrate via drilling, percussion-based investigation techniques, sonic vibratory drilling methods, and various static direct push cone penetrometer testing or CPT. That is all for my part. I hope that you enjoyed it. Papasa ko na sa mga klase ko.
The next section will discuss the main types of geotechnical failures that occur in open-cut coal mines. In excavated slopes, these include planar, wedge, toppling and composite failures. In dumped material, these include active-passive wedge failures. Failures that may occur in both excavated and dumped slopes include circular failures and isolated rock fall failures. Planar failure. These types of failures occur where a block of rock slides along a single defect that dips and daylights in the excavated face. Wedge failure. Wedge failure occurs where two continuous planar defects intersect and daylight in the excavated face. Toppling failure. Toppling failure occurs when persistent defects dip steeply into the excavated slope and the blocks or columns formed topple out of the face. These failures generally have a weak layer at the base that the vertical blocks slide along. Composite failures. These are typically the most common type of failure in excavated coal mine slopes. Composite failures involve a combination of planar, wedge and toppling failure modes along persistent defects, and also some component of rock mass fracturing and failure. Typical composite failures are vertically to subvertically bound by structural defects and horizontally bound by a weak, generally carbonaceous layer. Such failures occur at both the individual bench scale or as a failure of the overall pit slope. Active-passive wedge failures. These type of failures occur in dumped slopes, particularly where the dump is formed on a weak and/or steeply dipping floor. Circular failures. Circular failures occur in highly weathered, soil-like or dumped material that contains little to no large rock fragments. Circular failures may be deep-seated or may occur near the surface where they are referred to as skin slippage failures. Circular failures typically result from an excavated or dumped slope that is greater than the angle of repose through undercutting or over-steepening mining practices. Isolated rock falls. These are failures in which individual rocks fall out of a dumped or excavated slope face. Isolated rock falls can be just as hazardous as failures involving a whole slope face. They generally occur after heavy rain events, where poor separation of dumped material has occurred, or where blasting has been poorly executed and the face not adequately scaled for loose rocks at the time of mining.
Once a geotechnical hazard has been identified, an inspection will be completed as per site requirements. Controls will then be put in place to effectively manage the hazard. Controls must be followed at all times. If you observe conditions to change from those documented in the site hazard report, notify your supervisor immediately.
Typical controls to manage geotechnical hazards using the hierarchy system include elimination controls, scaling or chaining of slope faces and crests to remove loose rocks, trim blasting to remove unstable ground, redesign or engineering controls, altering the blast design, such as changing from a hard wall to a soft wall, installing temporary buttresses, reviewing and redesigning the mine plan, such as incorporating additional benches into both excavated and dumped slopes, only allowing equipment with falling object protection installed to work within the hazard zone, separation or isolation controls, controlling access at the crest or toe of the identified hazard by installing hard barriers, restricting to single lane access past the hazard, limiting equipment used in the hazard zone, such as allowing the excavator arm and bucket only inside the hazard zone, or modifying or restricting the dragline dig sequence to minimise exposure to the hazard, regrading or re-establishing tip heads, rectifying drainage conditions, including installing pumps and grading slopes away from the crest into a sump. Administration controls. Increasing the frequency of inspections, allowing only experienced operators within the hazard zone, completing additional risk assessments for specific mining sequences, such as mining on retreat or backfilling after mining coal, establishing monitoring controls, such as peg telltales, wireline extensometers, prisms, LiDAR or slope monitoring radars, restricting operations to daylight hours only, or installing additional lighting. The number and nature of controls is governed by the consequence and likelihood of a slope failure occurring. slope monitoring and implementation of standoff zones are two of the most commonly applied and effective controls if managed correctly. Slope monitoring is completed by one or more of the following methods: visual inspections, peg telltales, wireline extensometers, prism monitoring, laser scanners, drone surveys, LiDAR or slope monitoring radars. Monitoring devices can be used for either long-term, broad-scale detection of slope movement or targeted monitoring of a specific area of concern. Regardless of the monitoring device implemented, it is important to remember the following. Monitoring devices deployed should be able to measure the direction and magnitude of slope movement. Monitoring backsite devices need to be mounted on stable ground, otherwise false or misleading measurements can be recorded. Monitoring equipment needs to be regularly inspected and serviced to ensure it is operating as required. Trigger or alarm levels need to be predefined and should be set at levels specific to site conditions. Standoff distances can be applied at both the crests and toes of excavated or dumped slopes. Standoff zones are typically based on empirical charts, past performance of slopes with similar conditions, or modelling results from software simulating individual rockfalls or slope failures. The applied standoff distance should be appropriate for the type, size, likelihood and consequence of slope failure. Many sites have standard restriction zones that are applicable at all times. Increases or decreases to these standard restriction zones are then made on a case-by-case basis depending on the specific hazards present.
So now, we will discuss what are the usual problems faced by geotechnical engineers. According to Wiley Online Library, there are three main types of problems faced by geotechnical engineers. These are failure load problems, deformation problems, and flow problems. On to the first type of problem, which is the failure load problem. This occurs when a load at which the pipe body or the connection will fail disastrously, as in an actual separation, a rupture, large permanent deformation, for example is buckling or collapsing, or massive loss of sealing integrity. Typical solution to the problem of finding a failure load, for example is the ultimate bearing capacity of footing, or a failure moment with an example of slope stability, is to use the limit of equilibrium analysis. Numerical solutions typically require the use of computer because of the complexity and amount of mathematics involved. Many problems in geotechnical engineering involve large movements or rotations. Examples include man-made processes such as earth moving and pile penetration, or natural processes such as landslide. The problem of large deformation often occurs in geotechnical engineering. Numerical modeling of such issue is usually complex and tricky. The chosen solution has to implicate soil-soil and soil structure interactions. So for our last topic, which is the flow problems, permeability is one of the most important physical properties of a soil, as some of the major problems of soil mechanics are directly connected with it. Design of highways, airports, earth dams, construction of foundation, the low water table, yield from a well, as well as settlement of foundation and other projects depend upon the permeability of a soil. Hence, to become a good soil engineer, the knowledge of permeability is very essential. A material is said to be permeable if it holds continuous voids. Since such voids are contained in all soils, including the stiffest clay, all these are permeable. Gravels are highly permeable, and stiff clay is the least permeable soil. So from the discussed topics, which is the failure load problems, the deformation problems, and the flow problems. These are the usual problems faced by a geotechnical engineers of our modern society.
And now, we will meet two geotechnical engineers, Dr. Amy Serrato and Engineer Pia Mavani. They will discuss what it's like to be a geotechnical engineer and their daily life as a geotechnical engineer.
Hi future engineers, my name is Amy Serrato and I'm a geotechnical engineer at the University of Oklahoma. Geotechnical engineering is all about the study of what happens underneath the ground and how what happens underneath the ground affects what we build on the ground. And so I worry a lot about earthquakes and flooding and high wind events and try to figure out how to build structures that keep humans safer from those elements. When I was in high school, I had never heard of engineering, and I had a junior level teacher who encouraged me to do an internship with a National Park Service. And so between my junior and senior years, I went down to Kentucky Cumberland Gap and lived backcountry for 6 weeks, and we had to revegetate trails, find our own water sources, and my group leader said, "Amy, I think you'd be a great engineer." That was the first time I'd ever heard the word engineer. And so from there on, I went to Lafayette College to study civil engineering. And when I got to civil engineering, I couldn't decide what I wanted to do. Structural, transportation, geotechnical, or environmental. And I had a female faculty member that taught my undergraduate soil mechanics class. And she was so phenomenal that I just was so interested in soil mechanics and foundation engineering. That is when I decided that I was going to graduate school to make a career in playing with dirt. A typical day at the university is meeting with students, teaching some classes, working in the lab on some research, and coming out here to the field and doing full-scale testing, which helps to validate our numerical models. When I first came to the University of Oklahoma, I was fascinated that we had something called expansive soils. Back east, everything is saturated, which means it has a high water table, and the soil stays relatively the same. When you come to Oklahoma, we have very dry climate, and the soil expands when it rains, and it shrinks when it dries. And so I became fascinated with trying to build foundations that would keep houses from swelling and shrinking during these wet and dry cycles. And so in 2008, I won a presidential award, which is the highest award that they give young career faculty in the country. And I got to meet with President Obama at the White House. And that work from expansive soils really led into a love of trying to design in all different types of soils to keep everything that we build on those foundations more stable and have a longer design life. I believe some misconceptions are that you have to be excellent in math. I believe you have to be competent in math, but you have to want to solve problems in this industry and be creative. And so I try to tell young people that if you have a really creative mind and you like coming up with solutions that aren't already known, you can be an engineer. You always have the ability to use the math you've learned, but we don't do math and differential equations every day. Well, as you can imagine, soil is not a transparent medium. We can't look down and see into the ground. And so we have to do some kind of testing to figure out what's underneath the ground. And so a challenge becomes, because the soil is so different step by step, is trying to have a big visual picture of what an entire field looks like. And so the challenge is to go from a plan view to maybe a profile view and to connect the discrete borings together to create a picture of the soil that you're going to build on. And how I overcome that is using some computer programs that will take the spatial data and meld it all together to produce this nice picture where I can see where there might be some problem spots in the ground where I need to design a different type of foundation or do some other kind of ground remediation to make sure the building or the roadway doesn't settle or develop potholes or bumps, so when you're driving down the road you have a nice smooth travel. I believe internships in high school and in college really helped me focus and narrow down on what I wanted to do. In fact, I think an internship is a really good way to figure out what you don't want to do. And so I encourage people to go out and take that chance and take that internship and do that stint in a national park or volunteer somewhere where you think you could help using your skills and decide if that's really what you want to do. I believe in a growth mindset, and I believe that we all have the ability to do whatever we'd like to do if we work hard enough at it. And so if you try something and you fail, you should try again until you succeed. Because I can always remember sitting down and trying to learn trigonometry and trying to learn AP calculus and having a hard time at first and thinking, oh, you know what, Amy, you're not good at math. But the fact of the matter was, it was so new to me, I had to spend a lot of time learning, and once I spent a lot of time and put the time in, it became easier and easier. So if something's hard, don't be afraid to fail. In fact, you should fail often, and I think a measure of a person's success is not that they don't fail, is that they fail a lot, but then figure out how to succeed from all those failures. So I really like to work with problematic soils, and Oklahoma is one of the states that has probably the worst soils in the United States. Like I said, we have expansive soils that swell when it rains and shrink when it's dry. And so that puts a lot of pressure on whatever we build on it. And when I moved to Oklahoma, I noticed that there's lots of cracking in buildings and people couldn't close their windows and the doors wouldn't open, and I wanted to try to solve that problem. And fast forward a few years, I became very interested in wind loading, because Oklahoma is a very windy state. And so here we are at Berge Wind Power, and this is one of my recent research projects, and it's trying to help Berge come up with an alternative foundation system for their self-supporting lattice towers. Self-supporting lattice towers, as you can see here, have 3 legs that come down, and they support a wind turbine that generates electricity for whatever you need electricity for. And they're residential turbines, and so we put them behind people's homes. And people like this type of self-supporting lattice tower because it's a small footprint and yet it creates a lot of electricity to put back into the grid. And so Berge asked me to come up with a foundation system that had no concrete in it, but would allow the wind load to get damped and get the maximum power out of their turbine. And so I used helical piles, which is a piling system that's a big soil screw that spins into the ground, and it's a very flexible pile that allows the tower to move without creating excessive movement at the turbine level. We also use these type of foundations in earthquakes to allow people to be safer and get out of their homes or off bridges before it collapses, because that helical pile has a lot of damping characteristics that take the earthquake and lessen its effect as it moves up through the ground. And so my students and I have been working on this. We have instrumented 3 different piles. The piles are 13.5 feet in the ground, and as you can see, the tower is up, and I have a solar powered data rig that is reading all of the data that's coming out of the ground. And last night we had a big windstorm, and you can look at the data and see where that wind came through, which is pretty exciting because not very many people have had the chance to instrument pile foundations underneath these towers. And so why I think this research is so exciting is because we can measure the dynamic loading of a wind tower, of a bridge system, of a gas compressor, and we can figure out how to keep these structures safe and producing whatever we've intended them to produce, whether it be wind power, whether it be collecting gas and gas refining or oil refining, or even keeping bridges from collapsing during earthquakes. And so if you come over here and look at these, we can see some of the instrumentation, which is covered by this plastic because of all the rain we've had. But we have accelerometers that measure the G-forces, and down underneath the ground we have a lot of strain gauges which allow us to see how those piles are bending under the wind load. And so we're hoping that towers like this and wind power like what Bergie is generating can be brought into smaller communities in China and Africa and rural America where they can't get concrete because it's too far away from the batch plants, and they can spin these helical piles in, put these towers up, and generate wind power that can provide water to their village and electricity to their houses. And these piles and systems are great because if you need to take them down and move them, all you do is take the tower down and then take a machine out here and spin the pile out of the ground, and you leave no trace that you were ever there, which I think is a great green alternative to a concrete foundation. Thank you for watching my profile. My name is Amy Serrato and I'm a geotechnical engineer. For more profiles, please visit yesscienceshow.com. Thank you.
My job title, I guess, is graduate civil engineer. I'm working with the geotech team. It's like a crash learning course for me. You know, just being, I guess, somewhat fresh out of uni, a couple of years experience, and working with a team of people who've been in the industry for over, 10, 20 years and who have seen it all, and it's privilege, really, just to be working with people like that. This job we're at the moment is called the Ringary Bypass. It's part of the Roads of National Significance and part of a section of the Waikato Expressway. NWH did the design on this section of the highway, the motorway, and we're currently working for the contractor just to help interpret our design. So as part of the engineer's representative role, we do a lot of inspections on the work that the contractors are doing, so sort of just checking that it's in line with the specification and in line with drawings and things like that, and then also deal with queries that come through from the contractors to the designers. So I guess you could say sort of a middleman role. Can be a little bit intimidating, especially when you walk into that first induction and you've kind of got 50 guys staring at you thinking, who brought their daughter into work today? Yeah, I love it. It's so fascinating, there's so much going on, and you see around, you've got your structures and a whole bunch of earthworks and dirt, which I love because I'm a geotechnical engineer. I'm Priya Mavani and I'm a geotechnical engineer with NWH Global.
To reiterate from the beginning, geotechnical engineers are a part of a branch of engineering. It's actually a specialized one, to be exact. And if architects is still making blueprints and designs, and computer engineering is still making or developing computer hardware and all that stuff, then geotechnical engineering is to dams, bridges, roads, and every earthwork you could possibly imagine. So in this portion of the video, I will be discussing to you or showing you some illustrations as to what do these engineers do for a living, or how do they contribute to the society in general. Later in the video, we will be showing to you guys some of the famous works of some geotechnical engineers that have been immortalized up until this date. But for now, let's focus on these two pictures. As you can see, the tallest skyscraper located in Dubai, the Burj Khalifa, is a collaboration effort of many types of architects and engineers, including geotechnical engineers. Also, the longest bridge in the world, the Danyan Kunshan Bridge, is located in China, which is the product of all engineers, like what I said, geotechnical engineers. I'm not gonna go into detail as to what makes these two creations wonderful in a sense. And I'm gonna be focusing onto you the job of the geotechnical engineers. So what do these two buildings or one building and one bridge have in common? Yes, they're very big and it has a lot of force that's going to be located at the bottom. What I'm trying to say is geotechnical engineers are in charge of making these things stabilized. From your houses, from your malls to your theaters and all such matters of buildings, they are all products of geotechnical engineers, because without them, everything would be another leaning tower of Pisa. Let's move on to slide 35. So geotechnical engineers measure the weight and density of the soil and then use some machines and contraptions in order to simplify their objectives in sampling the ground. So to put it short, basically they are the taste testers in construction industry because they are scouts, to be exact. So if Attack on Titan has like the survey course where they seek out like areas where they can see useful supplies and all that such. In construction, on the other hand, they are the ones surveying on the ground, and that through them, we are able to identify what type of foundation should be built. Because remember, everything is changing. That's what calculus is all about. That's why we're talking about calculus. So as geotechnical engineers apply the laws of calculus, let's say by measuring the breaking capacity or bearing capacity, rather, the shear strength of the soil and slope stability, the lateral earth pressure, and all other geotechnical engineering technicalities that should be mentioned, but I can't. Well, to put it simply, they are scouts before making buildings. So what do the geotechnical engineers do after they have tasted or analyzed the soil in a construction site? That's correct. They plan on their analyzation skills on how to make or plan out what the foundation would look like or what it would compose of. So what are foundations exactly? Actually, it's very simple. They are like a structural system underground. Let's say it's a piece of Jenga, or let's say we're playing Jenga, and that in the game you have to at least take one wooden block from any area and make the building as stable as possible without it falling. And if it falls, you lose. So basically, that's what foundations are. They make the building stable. And as we all know that Philippines is located in the Pacific Ring of Fire, we can reduce the amount of damage that these buildings would get or generate. So in short, foundations are supports or anchors of a building that transfers their loads evenly to the soil. Of course, analyze soil. If we put it on like an unknown ground or soil type, then it will be disastrous. Trust me, you don't want to do that. So to put it more simply, let's make it more simple, shall we? So imagine you're the support in a team. So basically, your job is to make sure that your teammates are getting healed and that they get more buffs like increased in attack or defense or magic, anything. As long as you can give support to your team, then you are called a support. That's what foundations are. Because without the foundation, a building is practically impossible. Or let's say the Burj Khalifa is impossible without solid foundations, because without them, it would be destroyed by the earthquakes or natural causes such as the moving or shifting of the tectonic plates. So let's move on to slide number 36. And as stated here, faulty or absence of geotechnical engineers can result in many roads and structures to be destroyed easily. So, like I have mentioned back on the previous slide, geotechnical engineers have pretty much important scouting abilities, such as the measuring of the density of soil using many contraptions, as well as making solid foundations, planning solid foundations, and such. And that without them, we won't be able to stand a chance in surviving from like falling buildings, like debris and all that stuff. So imagine, let's apply Valorant here for a second, yeah? So imagine a breach just used his ultimate went like, let's go, yeah? And it completely destroyed the roads. So that's where geotechnical engineers come in. For damage report, they go and analyze what went wrong, the composition of the earth, the roads, what it's made out of. They're basically analysts. So they have knowledge about geology also. They won't be called geotechnical engineers if they don't know like earth related knowledge and all that stuff. So trying to piece this out, geotechnical engineers are basically not supposed to be absent if you are going to go and urbanize a certain part of the country, because without solid foundation, without solid analysis on what the earth is there like, or what the behavioral patterns that have been occurring there lately, then it's safe to say that you shouldn't be making a building there in the first place. As you can see, engineering isn't a one-man team only. It's a team effort of multiple engineers uniting as one in order to make the impossible possible. As I have mentioned previously before, they studied the earth simultaneously with calculus in order to apply the rates of change as well as physics on how buoyancy works if it collided with land and all that stuff. So as stated here, the study of earth allows them to understand how particular plot of land behaves as well as prepare for natural disasters. As you can see from the bottom right, they have labeled some parts of land there in order for them to identify what variable would be affected if something were to happen, like natural disasters, floods, tsunamis, natural landslides, or earthquakes. So yeah, they actually make a rigorous process in analyzing the soil because it can sometimes be tricky. As we all know that soil can be different in other places, even though it's from the same island or continent in general. So what do they mean by prepare for natural disasters? Well, as they have stated there, they can analyze what type of natural disaster might occur in a specific area. They take the soil samples, of course, they analyze, they carbon date, they do whatever it takes in order to give or get accurate results in general. They analyze also what problems are going to be occurring once that natural disaster has occurred. Of course, it wouldn't be natural disaster prevention without them making any alterations to the surrounding land whatsoever. After they have analyzed the surrounding area, they go and formulate many evacuations or try to give experience to the locals on how to keep themselves safe during, let's say, a storm or an earthquake. They try to generate disaster plans, in short. And to sum it all up, geotechnical engineers are the earth benders in real life, in which after they have carefully studied the soil, they are able to make solid foundations for the buildings in order to be stable, as well as make plans for natural disasters. They are basically unstoppable forces.
Hello again, everyone. So for this portion, I will be discussing some of the famous works both done internationally and locally here in the Philippines. To start, I shall share with you the first one, which is the international work, the Leaning Tower of Pisa, or Torre Pendente di Pisa. This tower was built in the city of Pisa in Italy on August 9, 1173. The construction of the tower itself took almost 200 years, and the architects that spearheaded the design and building of the tower were Bonanno Pisano and Gherardo din Gherardo. The tower itself was originally built to be a bell tower for the cathedral complex that was recently built that time. But shortly after it was built, it was deemed unusable due to the lean that started to form. The tower stands at a whopping 185 feet and is made out of white marble. For the second portion, I will be discussing some of the reasons and factors that constitute as to why the tower leans. So let us watch this video recording that explains some of these factors. That recording only explains some of the reasons as to why the tower leans. In addition to this, there is also an external factor that affected the lean in the tower, which is the plan to level both sides. There was an engineer named Giovanni De Simone that tried to add more stories to the sunken side, which resulted to a much less favorable lean. Aside from these reasons, one of the biggest contributors to the lean in the tower is its geological location. The tower's location was near the seashore. This causes the subsoils under the tower to absorb water. Thus, sedimentation happens on the north side, which results to more organisms residing on the north side, thus making it appear higher than the south side. And in addition to this, according to engineers, the analysis of engineers, there was also a problem regarding the soil on the south side, wherein the tower leaned towards to. They found out that the soil on the south part was significantly softer and clayey, and the sand was thinner than that of the north side. This shifted the weight towards the south part. To move on to the next work, we now focus on local works done here in the Philippines. So the famous work we decided to present is the Philippine Arena. Stationed in Bocaue, Bulacan, the Philippine Arena was constructed in 2011 and finished in 2014. It is considered to be the largest indoor stadium in the world. The engineer for the project was Buro Hapol, and the architects were from Pompilus, a global mega architecture firm. This project was funded by the Iglesia ni Cristo, and the design concepts were inspired by a Nara tree, the root of a banyan tree, the Nipa hut, and a Greek amphitheater. The arena itself also resides 27 kilometers from the West Valley Fault, which puts it in quite a predicament in a difficult situation should a strong earthquake occur. So, the plan was to build a complex that was able to fit 50,000 people inside and another 50,000 people outside. But the problem lied in the strength of the complex. It should be safe enough in case of emergencies. In order for this to happen, the foundation it was built on should be firm and sturdy. Thus, the ground was dug and reinforced with steel to make it stable. Moreover, the ceiling frames were divided into 46 parts and then constructed on the ground, then brought up on the steel frames, making them lighter. to minimize debris falling that causes accidents. Being considered one of the top 5 most earthquake-resistant buildings in the world, the Philippine Arena should be able to speak for itself. So, Burro Happold made the design so that its seismic design could withstand earthquakes ranging from magnitude 7.0 to 7.5. This is due to the lower part of the arena that can bend and sway and still not break because of the lead rubber bearings that acts as an absorber for the shock. Within its design also contains the topography planning that help in making better decisions regarding on what to use so that the foundation might be better.